Hi, for this part of the lesson, we're going to look at applying the technique of samarium neodymium dating. And we're going to see the effect it can have on the accuracy of the dates that we get. For this, we're going to look at a geological body called the Ballantrae Complex. This is on the west coast of Scotland, looking right on the Firth of Clyde, looking out to the island there of Ailsa Craig. You'll need for this your samarium neodymium Ballantrae handout and a calculator. Okay then, let's go. Now the Ballantrae Complex is a group of metamorphic and igneous rocks that were originally oceanic crust. When there was a collision of two continents during during an orogeny, it got scraped off the oceanic crust and is now part of the continent. It's part of a type of rocks we call an ophiolite sequence. We don't need to worry about that too much, but the type of rocks we find within that will include oceanic crustal rocks. Rocks, for example, like basalts and the pillow lavas that you can see exposed in this outcrop in this photo. Because we have a lot of igneous rocks and metamorphic ones, we can date these rocks. And in particular, with these ophiolite type rocks, if we date the metamorphism, that dates for us the start of an orogeny. This is a map of the complex. You can see its location there in southwestern Scotland. Now, back in 1980, there was a potassium argon date undertaken on hornblende from this complex, and it gave an age of 478 plus or minus 8 million years. So about a 16 million year window in which the metamorphism occurred, and with it the start of this orogeny. What I'd like you to think about, firstly, is to calculate the percentage error for that date. What percentage uncertainty is there for that date? Secondly, what geological period did this happen in? You may need to go back to your geological column homework that you did. And finally, which orogeny are we actually trying to date here? Okay, have a go at those questions. We're going to come back to the answers shortly. You might want to press pause now to have a go at those. Okay, this is a very simple map of parts of the Ballantrae complex, and it illustrates some of the relative ages we're talking about here. Now you have a graph showing the isochron for the metamorphism of the Ballantrae complex. What I'd like you to do now on that graph is sketch the isochrons for firstly the pillar lavas, and secondly the basalt dike. Sketch those onto your graph. You could use different colours, label them up, but show us where those where they will come on that isochron graph with samarium neodymium dates. Have a go at that now. Again, you might want to press pause again to have a go at that. Okay then, let's see what we've come up with. This is the actual graph used for the dating. Trying to interpret this graph from the numbers is quite tricky. So I don't think that's likely to come up in an exam. Anyway, let's look at some answers. If we draw on the isochrons, we could see from the map that the basalt is younger than the metamorphism. We've got a cross-cutting relationship there. Because it's younger, the isochron must be below the one that's drawn there for the metamorphism. We can see, though, that the pillow lavas were actually metamorphosed. So therefore, they must be older than the metamorphism. So the isochron for those must be higher. If we look at the percentage errors here, we have a more recent date. So from 2017, a Sumerian Neodymian date for this metamorphism gave an age of 477.6 plus or minus 1.9 million years for this metamorphism. So what I'd like you to do now is calculate the percentage error for that date. How much more accurately was Sumerian Neodymian able to date this event compared to potassium argon? So how does it compare? Okay then, let's have a look at some results here. If we look at potassium argon, if we think about the percentage that 16 million years, remember it's a plus or minus, so plus or minus 8 gives us a 16 million year window. That 16 million years is 3.3% of 478 million. So we've got a 3.3% error for potassium argon. This occurred during the Ordovician period, and it dates the start of the Caledonian orogeny. Now for Sumerian Neodymium, we've got a 3.8 million year window for our date, which gives us an error of 0.8%. Now, if we think about the significance of that, that means there's 4 times more accurate. There's 4 times less error in that date. Although what's quite impressive is that the two actual midpoints of that date are actually very, very similar. But we can have far more confidence in that using Sumerian Neodymium than we can do with potassium argon. That's why it's used. If we show this graphically, what we see is these two dates. So the potassium argon date of the hornblende there gives us quite a wide error bar, going from about 470 million years up to about 486 million years or so. But the Sumerian Neodymium date on the garnet gives us a far more accurate date. And we think these represent the start of the Caledonian orogeny. So, If we think about the strengths of this particular technique, these ratios that are measured uh, aren't really affected by other processes, weathering, metamorphism. These things, stay fairly consistent. We've got an enormous half life. These things aren't going to run out. It means we can date both terrestrial and extraterrestrial. We can date meteorites with this. They are rare earth minerals, but we do find them in lots of different minerals, but in small quantities, but enough that we can measure. And crucially, they give us accurate dates. We've just assessed how much more accurate. Make sure that you are able to add this information to your handout. You will be, or you can be asked to evaluate these different dating techniques that we use. Carbon-14, potassium-argon, samarium-neodymium. So, as we watch the sunset of Elsa Craig and see conclusions in Lallands, let's just sort that out. This technique is a powerful tool to give us an improvement in the accuracy and reliability of dates. In particular, when we compare it to potassium argon, it's far more reliable. We don't have the same issues as we do with potassium argon of loss of daughter elements, and with it, those anomalously young dates. It's a really useful technique. What we need to do now is think about some of the other techniques that we can use for dating to help us back up this particular technique, particularly when it comes to looking at sedimentary rocks. But that's for another lesson. I'll see you then.